Hello, everyone. Welcome to today's Rolled Alloys webinar. Today's topic will be going over best practices when using duplex stainless steels. Today's agenda will include a Rolled Alloys company overview. We will talk on metallurgical quality of base material and the welded joints. We'll talk on some base metal manufacturing recommendations, as well as some welding recommendations, and then questions, which we would like everyone, whoever has a question within the presentation, please feel free to throw it in the chat, and then we will address all of those at the end. Rolled Alloys overview. Here at Rolled Alloys, we are a global supplier of specialty alloys, and we also offer value-added services such as a state-of-the-art material processing. We have an e-commerce site, and our metallurgical expertise. Our expertise lies within nickel alloys, stainless steels, titanium, and cobalt alloys. We also get into various product forms ranging from plate, sheet, bar, and other round products. Continuing on that Rolled Alloys overview for our state-of-the-art processing, we offer laser, plasma, water jet, some bar saw cutting, and other types of fabrication or cutting that you might need. Our metallurgical services, we have a failure analysis lab. We provide a knowledge and those laboratory services for our customers as a value-added services free of charge. We also offer technical assistance. We offer laboratory services, lunch and learns, and also a sample inventory program. And today's speaker is Dr. Glenn Byrne. Dr. Byrne obtained his bachelor's and his PhD in metallurgy from the University of Sheffield. Dr. Byrne's professional qualifications include being a fellow of the Institute of Materials, Minerals, and Mining, and also a member of the Welding Institute and a chartered engineer. Upon finishing his degree, he joined the Corrosion and Protection Center for Industrial Services at UMIST in 1984. In 1989, Dr. Byrne joined Veer Materials and Foundries, contributing to a diverse global market and industries on application development and sales of duplex and super duplex stainless steel. In 2008, Rolled Alloys acquired Veer Materials and Foundries, where Dr. Byrne continued his work in market development and sales of duplex stainless steels. Dr. Byrne's professional interests lie in physical metallurgy, particularly in comprehending the intricate relationship between manufacturing methods, the microstructure, properties, and the applications of steels. Dr. Byrne is also very passionate on understanding the mechanisms of steel behavior and those reasons behind those failures and how to explore avenues for improvement. And I will be passing you guys along to Dr. Byrne for today's presentation.
Thanks for the introduction, Garrett. Well, and good morning, ladies and gentlemen. Today I'm going to be talking about metallurgical quality of the base materials and welded joints. Starting with the base materials. Duplex stainless steels consist of two phases, ferrite and austenite, and they're in roughly equal proportions in the steel. This image on the left here is the transverse section through a plate that's been polished and etched to show these two phases. The ferrite is the darker of the two phases, and the austenite is the lighter of two phases. The austenite is relatively weak, but it's very tough, and the ferrite is very strong but rather brittle. So by metallurgically engineering roughly equal proportions of each phase, you get the best combination of strength and toughness. Also, by alloying with enough chrome, moly, and nitrogen, you get good corrosion resistance. And it's that combination of properties that make these steels so attractive. But if something goes wrong in manufacture, third phases can be formed in the microstructure. And if you look at this picture here, these dark particles that you see are the third phases that I'm referring to. And they're called intermetallic particles, of which sigma phase is the most common. And these particles destroy both corrosion resistance and toughness. This is an example here where we show two corrosion test coupons that have been exposed to ferric chloride solution at 50 degrees C for 24 hours. Now, the acceptance level for that test is a weight loss not exceeding 4 grams per meter squared, and there should be no visible pits at ×20 magnification. Well, the pit in here is clearly visible and gross, and the weight loss that we measured was 435 grams per meter squared, and that's as a consequence of sigma in the microstructure. Also, when we did impact toughness testing of this material, we got 15 joules at -46. Now, the acceptance level is typically 70 joules at -46, and for a structure like this, we would really expect toughnesses in the region of 150 to 200 joules at -46. So you can see that these properties are significantly deteriorated if sigma's present in the microstructure. Now, the problem is if something goes wrong in manufacture, these third phases that are formed, we've no idea that they're there unless we test for them. We don't know there's anything wrong with the steel until something bad happens, like it corrodes or it cracks. So we use metallurgical examination of polished and etched sections, like you see here, and toughness and corrosion testing to confirm freedom from these deleterious phases on a cast and batch basis. Now, the ASTM product standards don't include requirements for these tests to be made. Here you can see for each product form, the product standards that are utilised, and they cover heat treatment, chemical analysis, actually tensile properties, dimensions, ND, marking, etc., but no requirement for microstructure checks, corrosion tests, or impact tests. Now, sophisticated users have recognised this, and they apply their own supplementary material specifications that are in addition to the requirements of the ASTM product standards. And these detail the methods of testing and acceptance levels that confirm the microstructural quality of the heat treatment batch tested and give confidence that the parts will perform as intended. Now, ASTM A928 or ISO 17781 cover this type of testing. But a word of caution. The occasional third phase particle is not necessarily a failure in the ISO standard, providing the material passes the other two tests. Now, we think that's a mistake. It's our view that the wrought and cast products that are to be further processed by welding should be certified as free from intermetallic phases at ×400 magnification by a competent metallographer. Because items containing small amounts of sigma can quickly contain unacceptable levels of sigma when subjected to welding. So let's talk a little bit more about sigma phase. The graph on the left shows the time and temperature ranges where sigma forms. That's this phase field here. So we solution heat treat super duplex stainless steels at about 1100 centigrade to homogenize the steel composition and to get the 50-50 phase balance that we seek. And then we quench it as quickly as we can into water so that we freeze in the desired microstructure. But we find that sigma can form in three ways. It can form isothermally if the steel gets held in the temperature range between 650 and 1000 degrees C, where sigma forms for a long enough period of time, then you'll get sigma in the parts. And the longer it spends in this phase field, you get more and more sigma. So if you just enter it, you get a small amount like you see here. You leave it longer, the particles grow and become more numerous, and you get a microstructure that you see here. It can also be formed during continuous cooling. So if during continuous cooling, the parts are sufficiently large to cool slowly enough to just clip the nose of this CCT curve or enter it significantly, then sigma phase will form in the part. The third mechanism is it can form as a consequence of repeated thermal cycles in the sensitive temperature range. And the time that's spent in this temperature range is cumulative, and the steel remembers its thermal history. So if you heat it up to the temperature range, spend a small amount of time, cool it down, heat it again in that range, spend a small amount of time, cool it down, all of those times at temperature become additive. And if they become sufficient in total to enter the phase field, then you'll get sigma. So as I say, the intention is to cool as quickly as we possibly can. So furnaces tend to be located very close to the quench tank, as you see here. And this is to minimize the transfer time from the furnace to the quench tank. The quench tanks should recirculate the cooling water through heat exchangers at a high rate, so the water is always cold. and the items being quenched should be agitated in the quench tank to minimize any steam jacketing and get cooling rates that are as high as possible. Now, generally speaking, the ratio of the weight of the water in the quench tank to the weight of the furnace load should be really generous. It should be about a ratio of about 10 to 1. Now, the thing to note is that, as you can see here, as thicker parts cool more slowly, so too do larger furnace loads. So the capacity of the heat treatment furnace and the quench tank has to be compatible with the size and weights of the parts being processed. So heat treatment and cooling rate during water quenching controls the metallurgical quality of these products. Now, in this slide, if you look on the top row, we see small well-neck flange forgings and butt weld fittings and some larger butt weld fittings packed into baskets ready for heat treatment. But the problem is, because of how the parts are packed into these baskets, the free flow of hot air between and through the parts during heat treatment is restricted. The efficiency of the water quench is going to be equally restricted. So parts on the periphery of the load may be okay, and if they're tested, they may pass. But parts in the middle of a load may well be metallurgically defective. Now, measurements using contact thermocouples in this particular case have shown that for parts in the middle of that basket, the proper soak temperatures and times are never achieved. The parts are heat treated in the temperature range where sigma forms and not where it dissolves. Now, the bottom row of photographs show a much better distribution of parts going into the furnace and the use of specialised supports and cradles to allow this. In this case, you can see this specialised basket containing well-spaced large diameter butt weld fittings, and in this case, this cradle is holding valve castings ready for heat treatment. Now, this demonstrates really that due diligence and the technical evaluation of a manufacturer's production capabilities and facilities is an essential step in vendor selection and securing quality of products. I'm afraid heat treatment and water quench is not necessarily the same thing to all men. So moving on from this, as well as cast and batch testing that we've talked about, microstructure, corrosion and impact testing, it's possible to check individual parts. Intermetallic particles are non-magnetic and they form and grow in the ferrite phase, and this reduces the ferrite content and ferromagnetic strength of the steel. So by using a calibrated device that measures the magnetic pull of the steel, this is called a ferritoscope that you see being used here, it's possible to detect parts with lower magnetic strength, and this is an indication that those parts could well be stigmatized. Now, typically these steels contain about 50% plus or minus 10% of each phase, so ferritoscope readings below 40 are a concern, and the lower the reading, the more concerned you should be. But this technique is prone to give some false positives or false negatives, whichever way you're looking at it, particularly over this intermediate range of readings. Generally, very high ferritoscope readings mean the fittings don't contain intermetallic particles. In this intermediate zone readings, some do and some don't. But generally, as the numbers get lower, there's a much higher probability that the parts are actually stigmatized. Now, you can map out on parts any areas of low readings like this chap's done here. And then what he's doing is he then polishes and etches an area locally within the low reading range, and then uses in situ metallography to look down this microscope at the part. If he sees any of those black particles under that microscope, he knows he's got a problem. He's confirmed the diagnosis of sigma phase. Now, this check has the benefit of being non-destructive, so the batches that are found to be stigmatized in the mill or in the warehouse can be recovered by reheat treatment. But this should only be done after a root cause analysis to identify and correct the errors in the heat treatment process that caused the problem in the first case. Now, some oil companies specify ferritoscope testing in addition to microstructure, corrosion and impact testing, and I consider that to be good practice. It's easier, less costly and less disruptive to do this and pick up any problems early rather than after fabrication installation, where this type of testing can be a painful experience, as you can see in this particular slide. So now let's talk a bit about welding related issues. I'm going to discuss nitrogen loss from the weld root. I'm going to discuss sigma in the weld metal, sigma in the low temperature heat affected zone, and secondary austenite in weld metals. So, despite all the talk about sigma, we find that over-purging of the ID of pipes with pure argon gas to avoid heat tints is the most common cause of failure in weld procedure qualification tests for first-time fabricators. The figure on the left shows the extent of heat tint that's formed at different oxygen levels in the backing gas, and that's just to give you a feel for what we're talking about when we say heat tint. Now, over-purging of the pipe bore causes nitrogen to diffuse out of the molten weld bead and into the pure argon backing gas. Now, nitrogen partitions to austenite preferentially in these alloys, so nitrogen loss lowers the corrosion resistance of austenite in the weld microstructure, and this causes the austenite phase to pit out during corrosion testing. This is a section through a corrosion test coupon that's pitted, and we can see here that austenite is preferentially pitting out, and that's an indication that we've lost nitrogen during welding. And you'll recall that the multiplication factor is a factor of 16 for nitrogen in the PREN equation, so it's a very important element for corrosion resistance. Now we can lose up to 20% nitrogen from the root run if we weld with argon shielding gases and argon backing gases in combination. The problem is resolved by not over-purging. Typically, fabricators are asked to purge to an oxygen content that's below 100 ppm, but some fabricators go very low, maybe down to 10 ppm to avoid heat tint. Now for super duplex, it's better to purge in the range 200 to 500 ppm oxygen. Heat tint in these grades isn't as troublesome as in 304 and 316 grade, and a straw-coloured weld's quite acceptable. You can also use argon nitrogen purge gases and argon nitrogen backing gas combinations to avoid nitrogen loss from the root run. Now, we can also get sigma in welds. It's possible to overheat the weld with excessive heat inputs into past temperatures and then form sigma phase in either the weld metal or low temperature heat affected zone, or both. In the case of the low temperature heat affected zone of the pipe, the 850 to 900 degree isotherm in the pipe is the location where sigma phase forms first and fastest. And this corresponds with the nose of the CCT curve that I showed you in the earlier slide where sigma forms fastest. Now, thin wall pipes with only two-dimensional heat flow tend to be more prone to this problem than thicker pipes. The issue really is conducting heat of the weld thermal cycle away from the joint as quickly as possible to avoid the nose of that sigma phase transformation curve. In multi-pass welding, you're continuously reheat treating, so the balance is to make the beads as big as possible without causing them to be sigmatized, and minimize the total number of weld passos and thermal cycles that take you up into the sigma sensitive temperature range. So if you can do that, you have a really good chance of avoiding sigma. Now, the required welding parameters and techniques to avoid this are really very well known. And this table gives some examples of arc energies, root pass thickness, and minimum interpass temperatures for different sizes of pipe. And this sort of information is available from very many welding company suppliers. Now we talk about secondary austenite in weld metal. We see preferential corrosion of secondary austenite or reformed austenite in welds. Now, the cooling rates in welds are very fast, so a first pass of a weld can be very ferritic because the austenite hasn't had time to fully transform. Subsequent passes cause more austenite to form, but the cooling rates are again still high, and the elements in the steel can't diffuse into their preferred phase quickly enough. So the austenite can be quite lean. Thermodynamic work has in fact confirmed that secondary austenite formed below 1050 centigrade is lean in chromium and particularly nitrogen. So it has a lower PREN than primary austenite, and hence the corrosion resistance is poorer than primary austenite. And you can see in this micro here, these stringers of the white phase are primary austenite, and they're retained in the structure. And these darker areas are where the secondary austenite has corroded in a ferric chloride test of a weld. So control of heat input into past temperature helps a lot to minimize this effect, but good welding technique helps too. Welding parameters that give a substantial thickness of first pass, followed by a second pass with a heat input about 20% lower than the root run, avoids reheating of that part of the root that's exposed to the environment. That's here. So the corrosion resistance is improved, and we call this the cold pass technique. Now this schematic is shown for 18mm thick plates, but it illustrates what we're trying to achieve. A decent size root run, reduce the heat input to the second pass, minimize the reheat treating of the root, and get good properties, unlike these other two cases. Now, just a few words on weld procedure qualification. It's important to qualify weld procedures and welders as being capable of achieving the microstructural quality in the joints. Welding procedures are usually qualified to ASME 9, but like the ASTM standards, this omits corrosion tests, microstructure tests, and impact tests. So these tests need to be included as supplementary requirements to the fabrication specification to ensure that the welding parameters and welding techniques used are good. We find that sigma phase formed by the fastest weld thermal cycles is not as detrimental as sigma phase formed isothermally in a furnace. Its size, shape and composition are not the same. So welds with small quantities of sigma phase can pass toughness and corrosion test requirements. Unlike for raw products, when applying the microstructure check as part of a weld procedure qualification, we've been inclined to accept some visual evidence of sigma in the microstructure, provided the corrosion resistance and toughness testing passed and the microstructure of these samples was the same as that seen in the original microstructure check sample. And this is the position adopted in the ISO 17781 standard. So let's just review this with some recommendations in relation to base material manufacturing. Use experienced suppliers or apply training and pre-production qualification with an appropriate level of production surveillance to new manufacturers. Use proven manufacturers with known heat treatment, quenching and pickling capabilities that suit the size range of the products being purchased. Now, what I'd say here is that some manufacturers have multiple furnaces, and not all of them are sufficiently good to give you the required heat treatment and quench properties of duplex stainless steels. So they need to use the proven and qualified routes, not other routes that aren't proven. Apply ASTM standard products, ASTM product standards with supplementary microstructure corrosion and impact testing to identify deleterious phases in the steel. Apply ferritoscope testing and in situ metallography to check individual parts or some percentage of them non-destructively. We've not mentioned this, but really apply PMI testing as well to avoid alloy mix-ups. All these stainless steels look pretty much the same. So you need to do that to make sure you're not mixing. Further welding recommendations. Use fabricators who employ qualified welding engineers. Let the welders practice, become familiar with the weld metal flow, welding speeds, heat inputs, and welding techniques required. Where possible, use fabricators experienced in welding duplex or super duplex stainless steel. And if this isn't possible, provide some basic training in the metallurgy of welding these grades before starting weld procedure qualification work, and suppliers will provide that service. So qualify welding procedures with supplementary microstructure corrosion and impact testing as part of the procedure qualification. don't accept pre-qualified procedures that don't include this testing. And I'd comment also that fabricators who experience some initial difficulty in qualification generally become better for having had that experience. And that's where I'd like to finish. Thanks for listening, and I'm happy to answer any questions or to the best of my ability that you may have. Thank you very much.
Questions, comments, or anything you'd like to say in the chat, please feel free and we will go over that and get back to you. Thank you all. Alrighty, Glenn, looks like we have a question. Question is from Jeff Warburton. Do you recommend the use of argon-nitrogen gas mixtures?
I think the answer to that is yes, we do, and people have used it extensively to basically pass ferric chloride corrosion test requirements on procedure qualification. What I would add is that these days consumables with a minimum PREN of 42 are available, whereas older versions had a minimum PREN of about 40.5, and we find that the PREN 42 consumables tend to be very robust in terms of corrosion resistance on their own, without support of argon and nitrogen shielding gas mixes.
Jeff says thank you, and we have another question here from Denise. I apologize if I said that wrong. What errors in fabrication would cause a high ferrite number?
It's very difficult, I think, to achieve that these days because the consumables are incredibly well balanced. But in situations where you weld in very thick components, the cooling rates in those passes that are dropped first can be very high, and so you can develop high ferrite contents in those regions. But subsequently, with subsequent passes, reheat treatment of those areas by the subsequent passes tends to get the austenite content up. But I suppose the issue potentially is if you've got like a tube plate weld, very thick tube plate, very thin tube, then in those cases the ferrite content can be high, and then again you can mitigate that with the use of argon nitrogen shielding gases. But as I say, these days it's mostly if you've got a very large heat sink and you're welding a small component to it with single pass welding, almost where you see most of the ferrite problems, and you can mitigate that with argon nitrogen shielding gases.
Alrighty, thank you. We have another question from Jeremy. On the impact testing of material with ASME required test on over 3/8 inch thick plate, since the suggestion is to also impact test pipe and fittings, should all thicknesses of plate be tested?
Generally, people don't test anything less than 6 millimeter thick, and I think effectively, I mean, the point is you're trying to pick sigma phase up with this. You're not trying to establish some criteria, some brittle fracture criteria. It's not a leak before break test that we're applying in this with these particular case and numbers. So I think 6 millimeter is a decent cutoff. At that thickness, it's relatively thin. It cools quickly, and it's not so thick as that brittle fracture becomes a problem. So I'd stick with the 6 millimeters that the international standards normally apply.
Alrighty, thank you. Another question, this one from Nick. Do you ever recommend autogenous welding of duplex and super duplex stainless steels, or should filler metal always be used?
Well, I'm a big fan of the filler metal. Having said that, we have very successfully welded tube joints together autogenously, but again, that's been supported by the use of argon nitrogen shielding gases in the torch. So no filler, fully autogenous, square edge butt in like 19.05 millimeter OD by 1.2 millimeter wall thickness tubes. And when we used argon nitrogen shielding gas, we got critical pitting temperatures in ferric chloride solution at 60 degrees C. So which is excellent. So I generally for normal welding autogenous no, but for tube welding then quite acceptable. The trick about this is just pass pass a qualify a procedure, and if you qualify a procedure satisfactorily, then there's no reason why you shouldn't go forward.
Thank you again, Dr. Byrne. All right, if there are no further questions, we will wrap things up here then. We'd like to thank you all again for coming. Please all enjoy the rest of your day.